My name is Geoffrey Spigule, and I'm part of the Wolfram machine learning team. And in this presentation, I'm going to show a couple of experiments that I've been doing on my side time during the last months, which involve like LLMs, large language models. So I will kind of divide the presentation into parts. One is going to be some experiments I did with LLMs playing the classic game rock, paper, scissors. And then we will explore the implementation of the BabyAGI, one of the autonomous agents that went viral, I think, at the beginning of the year. I think it was in March. Using GPT-4 and GPT 3.5 Turbo. So this image was generated yesterday using DALL-E 3. So the idea is that we will try to build some Wolfram language functions in order to make GPT-4 play against GPT 3.5 Turbo and against humans. So, but before we start, I wanted to kind of show some, or like make clear some kind of features of the large language models, or in this case, the GPT generative pre-trained transformers, which are decoder-only transformers. This is the architecture. And one fact that some people don't know is that these LLMs actually can be deterministic at zero temperature. So the concept of temperatures, it's important to have it clear. Sometimes we have it associated that as the LLM being more creative at higher temperature and less creative at lower temperature. But the hyperparameter comes from the softmax function. So this is in the latest one of the latest layers in the decoder transformer block. You have the softmax, and then we add a hyperparameter, which is known as temperature, from the connection to the physical temperature from the Boltzmann distribution. So basically, we can see it as a system where at lower temperature we have the probability one at having one state. In our case, it's a bit different. We have a number of tokens or words from the vocabulary, and this distribution gets at zero temperature. We only kind of promote one of those tokens. So it's the LLM behaves like a 100% deterministic. In reality, it's a bit different. Even at zero temperature, large language models such as ChatGPT and GPT-4, we will, for like generating long pieces of text over and over, we will get different results due to some technical issues in the GPUs. But in theory, those are like kind of deterministic models. So, for example, here I'm using LLM synthesize to make ask to generate randomly between 1 and 2, and requesting it 10 times in this case. And at zero temperature, GPT-4 is always giving me 2. But when we increase the temperature to 1, we start getting a bunch of 1s as well. So that was like kind of the main idea, that we are going to run these experiments at zero temperature, so they are kind of more or less deterministic, so we can reproduce the results that we're getting from these LLMs playing rock, paper, scissors game. So here the idea behind, I think I ran some of these experiments while doing the Wolfram Summer School last June and July. And the idea was to create a prompt that was the same prompt for both players. In this case, the same prompt would be used for GPT 3.5 Turbo and as the GPT-4. So after some iterations, the initial prompt that we ran was the following. So in this case, I was using LLM synthesized, but we will see later that in the second prompt, with some variations, I'm using LLM function as well. In this case, we are like defining, like explaining that it's an AI agent playing rock, paper, scissors games, explaining the rules, just to make sure that there is no misunderstanding there, and also that they're going to play 20 games or rounds in a single match, and the objective is to win the match. So, and then I'm showing them the previous games that they have been playing, from the last to the from the first to the latest, and here it was for doing the few shot learning. It was zero shot learning. I'm not showing this, and sometimes it answering one of these three move or plays, but then also like end up being verbose and maybe explaining why it should use that player or not. So this little extra capital letters sentence was helping. So I'm defining the agent with these two parameters. One is the association here with the plays. I initialize without any play, but then running once, you get the answer from the agent, in this case GPT-4, and then GPT 3.5 Turbo also. Then the idea is that I will use this kind of place, add them into the kind of the tracking of both players, and at the end, using kind of these helper functions, I will end up having again the association with the extra plays for each round. So then defining the kind of player a game. Here I'm defining, of course, since I'm using the same prompt, I need to swap the players in the association, so they are seeing the exact same prompt but with a different plays. And at the end, we have something like this, that one round playing it. So they are actually not seeing each other move before the other. So they only see the previous move that they did. And then once we have this function, we can use the nest function and run the experiment for 20 games. And then we can analyze the results with these couple of custom functions to generate a pie chart. In this case, Alice is the GPT-4, and Bob is the GPT 3.5 Turbo. And the same, we can do another visualization using a list line plot, for example, for the game number over time, and whether and the number of wins for each player. So we can see here that there's like some draws, and then Bob is winning a bit more, and then Alice, which is GPT-4, catches up. And at the end, GPT-4 is it's taking advantage of GPT 3.5. So now what we did is to initialize the game with the different possible game states. In this case, all one round of all different all the 9 possible conditions, and check the results from that initial games. So actually, they are playing only 19 games out of the 20 here, and this is a way to visualize the different from the move from Alice and Bob, and we can clearly see that GPT 3.5 Turbo, so the Bob, for some reason is kind of only running some rocks at the end, and kind of GPT-4 Alice is just taking advantage of it and smashing it at this particular game. We can check other configurations, and overall, typically in this case there is a draw. They end up having the same number of wins, but typically Alice managed to win Bob. Again, with paper and scissors, and here it's one of the only 9 initial conditions where Bob manages to be. But then doing the overall results, we can see that Alice GPT-4 is much better than GPT 3.5. Yeah, so here, so like adding all the results together, we get kind of, I think it's around like 40% win rate for Alice and 20% win rate for Bob. Now I tried a different prompt. In this case, I'm not going to use an association, but a list of association, which each of the rounds or game numbers. And in this case, the LLM will see next to their play from previous plays, the opponent's plays as well, and the game result. So the idea is to also make sure that using a different prompt, the results are more or less the same. In this case, I also changed it, the LLM synthesized into an LLM function, which is equivalent to the one that we had. But now the prompt is a template, an LLM prompt, where there is like a template slot. And so we need to add the played games in a different way. But mainly it's the same as before, just that the played games is now a list of associations, not as an association. All right, so I'm modifying a bit the player game. In this case, we don't need, so it's more or less the same, but just adapted to the new structure of the played games for tracking the games so far. And again, the results are like similar. So you can see in the first configuration, there is a draw, but then overall, Alice is winning against Bob, against ChatGPT or GPT 3.5 Turbo in this case. Yeah, I think there is also one configuration where Bob manages to win Alice out of the 9 different ones, but overall is again losing, and later we will see why, or partially we will be able to explain why GPT 3.5 is much worse than GPT-4. So yeah, in this particular case, when we start the first round with Alice and Bob both kind of throwing scissors, they end up, Alice ends up losing against Bob. It's in the so the overall results, again, it's around like 40% for Alice GPT-4 and 20% win rate for Bob. And if we look at the counts of the different move or plays for each player, we see that GPT-4 Alice is playing much more paper, and the explanation is that because Bob is not playing scissors at all, almost just like 4 times out of all the different games. So Bob likes rock. LLMs, and then I did some experiment, just like, okay, let's see how good is GPT-4 against a human. In this case, I only play it myself, but in the notebook you will be able to also run this kind of code and also like initialize this, manipulate and play against GPT-4 or the LLM that you want to play against using LLM synthesize or LLM function in this case. So I think in both cases, the different games I played, I was able to. So the Bob here is the human, and Alice is the GPT-4. I was able to kind of more or less predict the movements or like changes of GPT-4 pretty well. I think basically they are like playing. So I think in this case, my last play was scissors. So they are gonna try kind of use something to crash the last play. So in this case, they're gonna I'm predicting they're gonna play a rock here. So if we're using paper, probably we're gonna win GPT-4. Let's see. Yeah. So that's kind of how I was. It seems that GPT-4 is only paying attention to the last move and trying to adapt to it. For this particular prompt, maybe there's some other experiments that we can do, changing the prompt or making it more intelligent. But so far, I think GPT-4 is not beating humans, at least at this game. So this is a reference for one of the largest human experiments, kind of playing rock, paper, scissors. I think it was from a Chinese university. So there's the link for those interested. But I think it's still not in a position that we can use GPT-4 to simulate humans for this particular game. Other things that I did not try, but could be also explored, is that I'm playing against sequence predict. Sequence predict is probably gonna win against GPT-4, and this is an example of using sequence predict to predict the sequence, the next move from a scene sequence of rock, paper, scissors. And another thing that I did not try much was to use other LLMs models. We could also do the experiment with Cloud2 or Palm from Google. And starting from Mathematica 14, you will be able to also use the Service Connect to Hugging Face and run different open source large language models like Llama 2 7 billion. And I was able to get a response that it will tell you the next move, but it was not changing. It was only like giving me rock all the time, even if it would clearly lose against the opponent that was using paper. And in these lines of using these simple kind of games for LLMs, there has been a recent benchmark called a Smart Play, where there's like different LLMs playing a bunch of different games, including rock paper scissors. They are using a different technique that, or the different strategy that the one that testing that they're exploring games for like assessing the kind of the reasoning capabilities of these large language models. So if you're interested, there is also a bunch of different papers and reviews on such kind of game theory and large language models. It's I think it's a hot research area where there's like a lot of experiments that one can run. And if you're interested in such experiment and you get some results, you can contact me. We are like with some Wolfram Summer School students, we are still like running some experiments for such games. So with this, I will start. I don't know how much time left I have, but the second part of my presentation is about the BabyAGI, which was a kind of an autonomous agent that came out at the end of March, I think. And it was using originally ChatGPT and GPT-4 for in a loop and completing task. So this image was generated by DALL-E 3 again. And the idea of the BabyAGI is that there is different sub-agents within it that would run, one would create, so the human will start adding a goal, an objective, and then from there the BabyAGI will kind of start create new task for the main goal, and then you will have an execution agent of the first task on the list. Then there's going to be a prioritization agent which will rank the relevance of the different kind of left task, and based on the result of the execution. And at the end, you will run it for several kind of loops, and you will get kind of a bunch of results. It's a quite easy way of running out of kind of OpenAI credits. So just be careful with running this system. But basically, originally it was created by of stars in GitHub, and it was written in Python. And the idea was that the code was not super large. I think he managed to decrease the number of lines of Python code up to 100 something. So I decided kind of, let's try to implement a Wolfram Language version of BabyAGI. And it was, I managed to shrink it up to like 50 something that we will see here. So I added kind of some like the semantic search memories using embeddings from the LLMs. In this case, I used Wolfram Language documentation examples. Originally, I used the packlets from Christopher Wolfram for getting the OpenAI embedding. But nowadays you can use directly the OpenAI service connection that we have built in. So the service executes, and OpenAI will get a similar embeddings. In this case, by default is the text embeddings other 0.02, And I think Open AI embedding function was getting by default another embedding model. I'm sticking to this one just because I run, I just like run embeddings for all the documentation examples back in May when I did this implementation. So here I'm sharing the nearest function I created with these embeddings and Wolfram Language documentation examples. We can test it, for example, with this task, create a 3D pie chart. And this nearest function will give us a couple of examples from documentation with code that we know that it's correct because it's from the Wolfram Language documentation. And then the BabyAGI will be able to have it as a reference for the task, which might be a bit different. So then there's the execution agent contains this LLM function with the prompt. This is the same exact prompt that original BabyAGI had. There is a couple of actually there's like 3 different template slots here. So there is the main objective set up by the user, the human. Then there's the context examples retrieved from this nearest function that I mentioned above with the Wolfram Language documentation examples, and then the context with the previously kind of executed task. And you can see that I'm using the distance function cosine, the cosine distance. Nowadays, the state of the art for such kind of retrieval systems, it's a bit different, but I think for this particular case was working well enough. And then there is the task creation agent. This mainly will create a bunch of new tasks based on the completed task and the result of the current task. And then there's going to be the prioritization agent that will reorder the list of tasks and put up the ones that seem more relevant based on the previous execution. We add all these single loop, and the main code is this part here, where there's the different steps of the BabyAGI are executed. And at the end, I was running a bunch of experiments like this one, like generating several automata examples. And I will just show one at the end because I'm running out of time. One about like creating a lecture using Wolfram Language code examples on geometry. So I was initializing the BabyAGI, then adding the main objective, which is creating this lecture about geometry using Wolfram Language. And then the final result was like running the whole BabyAGI loop for like 4 times. And I was getting a bunch of different kind of lectures with Wolfram Language code within it. And I think at the end I have like some examples that it created using this system. And at the end, also we can check the number of different tasks or kind of sub lectures that was also creating for the. So if I was like running it for like many other editions, it would like pick up some of the. I would like to thank my colleagues at Wolfram and also like Wolfram Summer School students and mentors and BabyAGI creator for some comments on how he created BabyAGI. Thank you. And now, if there are like some questions, I will try to answer them. Right. So I see. That's a good idea from Anton. It's something that we also contemplated. I did not implement the rock, paper, scissors plus Lizard and Spock. That's certainly a fun experiment to extend what we have. And yes, yeah, if you are interested in such work, we can connect and run extra experiment. Maybe I think I will try to publish a Wolfram community post about it, and that would be like a nice way to have some more experiments on this. Then there's the question about hacking phase. Yes, it will be supported in version 14, and for the smaller models, the 7 billion models, some of them are going to be able to be run locally using users' GPU, depending on the system. But for example, even like 7 billion Llama 2 chat, I think it's too large for most of the laptops, for example. I think it's, I don't know how many gigabytes is it, but it's quite many, more in the order of almost 100 gigabytes. And then why I use a temperature 0 for BabyAGI implementation. I think the reasoning here was whenever since I wanted to also like write some Wolfram language code, typically when what we experimented is that for writing Wolfram language code per se, or not just Wolfram language code in general, lower temperatures is better. Doesn't mean that 0 is the best, but typically close to 0, like 0.1, works better for reproducibility. Typically, when you start with a sequence of tokens for describing a code, you don't want to be too creative. Otherwise, you will get some errors with brackets or some other symbols. Yeah, it's probably for being creative on other task or objective. BabyAGI needs to have a bit higher temperatures. So that's right. Might not be the best. And yeah, I think today and tomorrow will be around, and I will be open to meet some of you and have some extra discussions about LLM experiments, playing games, and autonomous agents.